Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we learned about the Coulomb's law and we also learned about the electric field intensity. So during our discussion, the charge that we have assumed was the point charge. But apart from that, we also have the continuous charge distributions such as the line charge, surface charge and the volume charge. So in this video, we will learn about these three types of continuous charge distributions and we will also take few solved examples related to them. So first, let us start with the line charge. So in case of the line charge, this electric charge is distributed continuously along the length. So for example, if we arrange the 10-point charges in a line at the specific distances, then that is not the example of the line charge, because in between the point charges there is no charge. So here this continuous charge distribution means this electric charge is distributed along the entire length. So here in case of this continuous line charge distribution, the charge is defined in terms of the charge density, and here since the charge is distributed along the length, so this charge density is defined as the line charge density, and often it is represented as the rho L or the lambda L. And if we see its unit, then it is defined in the coulomb per meter, that is the charge per unit length. So if we take the differential length dl on this line charge, then the differential charge dq along this length dl can be given as this lambda L times dl. That means if we multiply this line charge density with this differential length, then we will get the charge along this differential length. So for example, if the length of this line charge is equal to L, then the total charge Q along the length can be given as integration of lambda L times dl along the length. That means if we take this differential length dl and integrate it over the entire length, then we will get the total charge that is represented by this line charge. So now let us take few examples related to it so that it will get clear to you. So let's say we have a line charge of the 5 meter, and here its line charge density is equal to 5 nanocoulomb per meter. So in this case, if we see the total charge Q, then that is equal to this rho L times L, where the L is the length of this line charge, and that is equal to this 5 nanocoulomb times 5. That means here the total charge along the length is equal to 25 nanocoulomb. So in this case if you see, then here this line charge density is constant. That means here we have a constant charge distribution along the length. And because of that, if we just multiply this rho L with the L, then we will get the total charge of this line charge. But every time it may not be the case. That means many times we may have the non-uniform charge distribution. For example, in the second case, this charge density is equal to Z square millicoulomb per meter. So here once again the length of this line charge is equal to 5 meter, and here it is located on the Z axis from 005 to 0010. So in this case, based on the expression of the charge density, we can say that as we move along the length, then the charge density will increase. That means here for the given line charge, the charge distribution is non-uniform. So in this case, the total charge Q can be given as integration of lambda L times dl, and this integration is along the length of the line charge. So here, since the line is located on the Z axis, so here this dl will be equal to dz, and here the integration limits will be from 5 to 10. So we can say that here for the given line charge distribution, the total charge Q is the integration of Z square times dz, and here the integration limits will be from 5 to 10. So as you know, the integration of Z square is equal to Z cube divided by 3, and here if we put the limits, then we will get this 1 by 3 times this 10 cube minus 5 cube, and that is equal to 291.66 millicoulomb. So here the unit is also very important. because here this line charge density is given to us in the millicoulomb per meter. So based on that, the unit of this charge will become millicoulomb. So if you see the high voltage transmission line, then that is the example of the continuous line charge distribution. So here, so far, the examples that we have taken for the line charge distributions were of the straight line. But it is not necessary that this line charge is always distributed along the straight line. So in general, it can take any path. So for example, this line charge distribution can be in the form of loop. So if you see the loop antenna or the charged conducting ring, then they are the examples of the line charge distribution along the loop. So in this case, let us see how to find the total charge. So let's say we have a line charge distribution along this loop. And here let's say this loop can be expressed as this x square plus y square is equal to 9. And this loop is located on the z is equal to 0 plane. So let's say its charge distribution is equal to 12 microcoulomb per meter. So here if you see, then this loop has the axial symmetry. That means here, to find the total charge, it is easy to represent it in the cylindrical coordinate system. So we know that in the cylindrical coordinate system, this rho can be given as square root of x square plus y square. And from this we can say that here the value of the rho is equal to 3. That is the radius of this circle. So here, if we see the total charge along the loop, then it can be given as integration of rho L or the lambda L times dl. And here, since we are already using the cylindrical coordinate system, so instead of the rho L, we are using the lambda L. And here, this differential length dl represents the differential length along the loop. Or basically, it represents the arc length along the phi direction. So we know that in the cylindrical coordinate system, this differential length along the phi direction can be given as this rho times d5. And here, the integration limits will be from 0 to 2 pi. So here, we can say that this total charge q is equal to integration of 12 times this rho times d5. And here, the limits of the integration will be from phi is equal to 0 to phi is equal to 2 pi. So here if you see, then this rho is also constant. That means these both terms can be taken out. And further we can write it as this 12 times rho times integration of 0 to 2 pi times d5. So here we know that the value of the rho is equal to 3. So we can say that is equal to 36 times the integration of the d5. And we know that the integration of the d5 will be equal to 5. And here the limits will be from 0 to 2 pi. So if you further simplify it, then the total charge q will come out as this 72 times pi microcoulomb. Because here this line charge density is given to us in the microcoulomb per meter. Therefore, here the unit of the charge will be equal to microcoulomb. So in this way, if we have been given the line charge that is distributed over the loop, then we can easily find its total charge. So now in this case if you see, then once again the line charge density was constant. But every time it may not be the case. So for example, let's say in the second case, this line charge density can be given as this 6 sin square 5 microcoulomb per meter. So once again, here the loop is described as this s square plus y square is equal to 9. And it is residing on the z is equal to 0 plane. That means once again, the radius of this loop is equal to 3. So in this case, let us find the total charge along the loop. So once again, this total charge can be given as this integration of lambda L times dl, where here this dl is equal to rho times d5. So if you put the value of the lambda, then this q can be given as integration of 0 to 2 pi this 6 sin square 5 times rho times d5. So once again, here this 6 and the rho are constant. So let us take them out. So we can write it as this 6 times rho times integration of 0 to 2 pi this sine square phi times d5. And here we know that the value of the rho is equal to 3. That means this q is equal to these 18 times integration of 0 to 2 pi this sine square phi times d5. Now we know that this sine square phi can be written as this 1 minus cos 2 phi divided by 2. So here once again let us take this 2 outside, and further it can be written as this 9 times integration of 0 to 2 pi this 1 minus cos of 2 phi times d5. So if we further simplify it, then we will get this 9 times this 5 minus the sine of 2 phi divided by 2 with integration limits of 0 to 2 pi. So here we know that the sine of 4 pi is equal to 0 and the sine of 0 is also equal to 0. So if we further simplify it, then eventually this total charge will come out as 18 pi. That means in this case, the total charge along the Q is equal to 18 pi, and here its unit will be equal to microcoulomb. So similar to the line charge, we can also have the surface charge. So the surface charge is a continuous distribution of the charge along the area. So here, since the charge is distributed over the area, so its charge density is represented as the surface charge density, and often it is represented using the rho s or the lambda s. And if we see its unit, then that is equal to coulomb per meter square. That is the charge per unit area. So if we take the small differential area ds over this entire surface, then the charge occupied by this differential surface area ds can be given as this lambda s times ds. And if we see the total charge over this surface area, then it can be given as the surface integration of this lambda s times ds. So now let us take few examples so that it will get clear to you. So let's say we have an area in the square shape and its surface charge density is equal to 10 nanocoulomb per meter square. So here let's say the length of this square is equal to 2 meter and this square is located at the origin. So for this given square, let us find the total charge. So here if you see, then the surface charge density is constant. That means if we multiply the surface charge density with the area of the square, then we will get the total charge of this square area. But here, let us find the same using the general approach. It is also applicable in the case when the surface charge density is non-uniform. So here, this total charge Q can be given as the surface integration of this lambda s times ds, and in this case, this ds is equal to this dx times dy, and here this lambda s is equal to 10 nanocoulomb per meter square. So further we can write it as this integration this 10 times this dx times dy, and here the integration limits will be from 0 to 2. That means here the x is varying from 0 to 2, and similarly the y is also varying from 0 to 2. So here since the 10 is constant, so let us take it outside, and further we can write it as integration of 0 to 2 dx times integration of 0 to 2 times dy. So we know that that is equal to this x with the integration limit of 0 to 2 and the integration of the dy is equal to y, and once again here the limits will be from 0 to 2. So that is equal to 10 times 2 times 2, and that is equal to 14 nanocoulomb. So that is the total charge of this square area. So in this case, the surface charge density was constant. But now let us take the second case where it is non-uniform. So in the second example, we have been given the cylinder which has the radius of 3 meter. And if you see its axis, then it is located on the z-axis. So for this cylinder, the z is varying from 0 to 4. That means we can say that the height of the cylinder is equal to 4 meter. And here, we have been also given the surface charge density of the outer surface of this cylinder. So that can be given as this rho times z square nanocoulomb per meter square. That means here the surface charge density of this outer surface area is equal to rho times z square. So now let us find the total charge that is covered by this surface. So once again it can be given as the surface integral of this lambda s times ds. So here, since we are dealing with the cylindrical surface, so we will use the cylindrical coordinate system. And we know that for this curved surface, this ds can be given as this rho times this d phi times dz. That means here, this q is equal to double integration of this rho times z square times rho times this d phi times dz. And here, if we see the integration limits, then here the phi will vary from 0 to 2 pi, while the z will vary from 0 to 4. So here if you see, then this rho is constant. So let us take it outside. That means this charge q can be written as this rho square times integration of 0 to 2 pi d phi times integration of 0 to 4 dz square times dz. And here the value of the rho is equal to 3. So we can say that here this q is equal to 9 times the integration of the d5, and we know that that is equal to 5. And here the limits will be from 0 to 2 pi. Similarly, the integration of the z square will be equal to z cube divided by 3. And here the limits will be from 0 to 4. So further we will get this 9 times 2 pi times this 4 cube divided by 3. And if we further simplify it, then we will get these 384 times pi, and that is equal to 1206.3 nanocoulomb, or further it can be written as this 1.206 microcoulomb. That means here the total charge that is represented by this outer surface is equal to 1.2 microcoulomb. So in this way, if we have been given any surface charge distribution, then we can easily find the total charge that is residing in this surface area. So similarly, let us take one more example based on this surface charge distribution. So here we have been given this triangular region, and the surface charge density of this region can be given as this 6 times xy coulomb per meter square. So here let us find the total charge that is represented by this triangular region. So once again, here the total charge that is covered by this triangular region can be given as the surface integral of this lambda s times ds. And here, since the triangular region is given to us in the Cartesian coordinate system, so in this case, this ds is equal to dx times dy. So in this case, once again, since the surface charge density is non-uniform, so we need to find the total charge of this triangular region using this integration method. So here, the area that is covered by this triangular region can be divided in the two parts. So one is this part and the another one is this part. So in the first part if you see, then here the x is varying from 0 to 2. So in this region if you see, then this y or the height of this strip is varying according to this line. And as you know, here the expression of the line can be given as this y is equal to x, because here when the x is 0, then y is also 0, and whenever the x is 2, then y is also 2, and moreover this line is also passing from the origin. Therefore the expression of this part is equal to y is equal to x. So from this, here we can say that this q is equal to double integration of this 6xy times dx times dy. So here the limits of the x will be from 0 to 2, while if you see the limits of y, then this y is varying from 0 to x. Because here when the x is 0, then the height of the strip is 0, and whenever the x is 2, then the height of the strip or the value of the y is equal to 2. That means here the y is varying from 0 to x. So further it can be written as this 6 times integration of 0 to 2 x times integration of 0 to x this y times dy times dx. So we know that the integration of the y is equal to y square divided by 2. So further it can be written as 6 times integration of 0 to 2 times x times this y square divided by 2 with the limits of 0 to x. And of course, here we will also have the dx. So further it can be written as 6 times integration of 0 to 2 x times this x square divided by 2. So that is equal to 3 times integration of 0 to 2 this x cube times dx. So we know that the integration of the x cube is equal to x to the power 4 divided by 4. And here the limits will be from 0 to 2. That means here for this first part, if we see the charge or this q1 is equal to this 3 times this 2 to the power 4 divided by 4, and that is equal to 12 coulomb. That means the charge covered by this region or this q1 is equal to 12 coulomb. So similarly, let us find the charge that is covered by this region. So let's say the charge covered by the second region is equal to q2. So this q2 can be given as double integration of the 6 times xy times dx times dy. So in this region if you see, then this x is varying from 0 to 4. That means here the limits of the x will be from 2 to 4. While in this region if you see, then the height of this strip or this y is varying according to this line. So in this region, how the y is changing, to find that we need to find the expression of this line. And it can be found as per the y is equal to mx plus c. So here if you see, then the m is equal to this y2 minus y1 divided by x2 minus x1. So in this case, the y2 is equal to 0 while the y1 is equal to 2. That means on the numerator we will have a 0 minus 2, while in the denominator this x2 is equal to 4 while the x1 is equal to 2. That means the m is equal to minus 1. So we can say that the expression of the y is equal to minus x plus c. Now here if you see, when the x is equal to 4, then the value of the y is equal to 0. So from that we can say that when the y is equal to 0, at that time the value of the x is equal to minus 4. And from that we got the value of the c, that is equal to 4. So we can say that the expression of this line is equal to y is equal to 4 minus x. So we can say that in this region the y is varying from 0 to 4 minus x. So now to find this total charge that is residing in the second part, we need to integrate this term. So once again that is equal to 6 times integration of 2 to 4 x times integration of 0 to 4 minus x times y times dy times dx. So we know that the integration of the y is equal to y square divided by 2. That means further it can be written as 6 times integration of 2 to 4 times x times y square divided by 2. And here the limits will be from 0 to 4 minus x. And of course here we will also have the dx. So if we further simplify it, then this q2 can be given as 6 times integration of 2 to 4 times x times this 4 minus x whole square divided by 2. So that is equal to 3 times integration of 2 to 4 times x times this 16 minus 8x plus x square. So that is equal to 3 times integration of 2 to 4 times x cube minus 8x square plus 16x. So if we perform the integration, then we will get this x to the power 4 divided by 4 minus 8 times this x cube divided by 3. And for the third term, we will have the 16 times this x square divided by 2. And here the integration limits will be from 2 to 4. So further if we simplify it, then we will get 3 times this 4 to the power 4 minus 2 to the power 4 divided by 4 minus 8 divided by 3 times this 4 to the power 3 minus 2 to the power 3. And for the third term, we will have this 8 times this 4 to this power 2 minus 2 to the power 2. So further if we simplify it, then this Q2 will come out as 20 coulomb. So in this way, the Q1 was 12 coulomb while the Q2 was 20 coulomb. That means the overall charge that is represented by the triangular region was the summation of these two charges. Or we can say that this Q is equal to Q1 plus Q2, that is equal to 32 coulomb. So in this way, if we have been given any type of surface charge distribution, then we can easily find the total charge that is represented by this surface area. So similarly, now let us see the volume charge. So in case of the volume charge, the charge is distributed continuously over the entire volume. And in this case, this charge distribution is represented by the volume charge density, which is often represented by the rho v or the lambda v. And if we see its unit, then that is equal to coulomb per meter cube. So in the given volume charge distribution, if we take the small differential volume dV, then the charge covered by this differential volume can be given as this lambda v times dV. And if we integrate it over the entire volume, then we will get the total charge that is covered by this volume. So let us take the couple of examples so that it will get clear to you. So let's say we have one cube with all sides having a length of a, and it is located at the origin as shown in the figure. So here for the given cube, its volume charge density is equal to 3x divided by a. So now let us find the total charge that is covered by this cube. So once again, here the differential charge dq can be given as this lambda v times dv, where here this dv is equal to this dx times dy times dz, because here this cube is given to us in the Cartesian coordinate system. So if we see the total charge q, then that is the volume integration of this lambda v times dv, and that is equal to this 3x divided by a times dx times dy times dz. So here if you see, then this 3 by a is common. So if we take it outside, then this q can be written as this 3 divided by a integration of 0 to a this x times dx times integration of 0 to a dy times integration of 0 to a times dz, because here the limits of the integration for x, y and z will be from 0 to a. So further if we simplify it, then we will have this x square divided by 2 with the limits from 0 to a. Likewise, the integration of the dy will be equal to y and its limit will be from 0 to a. And similarly, the integration of the dz will be equal to z. So if we put the limits, then we will get this 3 divided by a times this a square divided by 2 times a square. So that is equal to 3 divided by 2 times a cube. And of course, the unit of the charge will be equal to coulomb. So we can say that the total charge that is enclosed by this volume is equal to 3 divided by 2 times a cube coulomb. So that is the total charge that is enclosed by the given cube. So similarly, let us take one more example. So in this case, we have been given this sphere whose radius is equal to 4. So for this sphere, the volume charge density is equal to 10 divided by r sine theta. So here, let us find the total charge that is covered by this sphere. So once again, here the total charge Q can be given as the volume integration of this lambda V times dV, where this lambda V is the volume charge density. And here, since we are finding the charge of this sphere, so we will use the spherical coordinate system. And as you know, in the spherical coordinate system, this dV can be given as this r square sine theta times this dr times d theta times d5. That means here, this total charge Q is equal to the triple integration of this tan divided by r sine theta times r square sine theta times this dr times d theta times d5. So further if we simplify it, then it can be written as the triple integration of this tan r times this dr times d theta times d5. So now here let us see the integration limits for all the three integrals. So here the r will vary from 0 to 4. Likewise, the theta will vary from 0 to pi. And similarly, if we see this azimuth angle 5, then it will vary from 0 to 2 pi. So by putting these limits, let us solve this integral. So further if we simplify it, then it can be written as these 10 times integration of 0 to 4, these r times dr times integration of 0 to pi times d theta. And similarly, we will also have integration of 0 to 2 pi times d5. So as you know, the integration of the r is equal to r squared divided by 2. And here, the limits will be from 0 to 4. Likewise, the integration of the d theta will be equal to theta. And here, the limits will be from 0 to pi. And similarly, the integration of the d5 will be equal to phi. And once again, here the limits will be from 0 to 2 pi. And of course, over here, we will also have this constant 10. So if we further simplify it, then we will get this 10 times this 4 squared divided by 2 times pi times 2 pi. So that is equal to 160 times pi square coulomb. And if we put the value of pi, then the total charge will come out as 1579.1 coulomb. So that is the total charge that is covered by the sphere. So in this way, if we have been given a continuous charge distribution, either in the form of line surface or the volume, then we can find the total charge. So now in the next video, we will see that how this electric field is generated because of this continuous charge distribution. And we will also see that how to find the electric field intensity at the given location. And first, we will start with the line charge distribution. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.